Hello, good afternoon to everybody. It's a pleasure for me to lead this discussion and this presentation this afternoon relate to the PRISM prize, which is the prize of the Institute of Structure of Matter of the National Research Council. It's an honor for me to introduce the winners. So the Institute of Structure of Matter awarded in 2021 two prizes, one in the senior category and one on the junior category. And today we will present this prize to the two winners. The first winner in the senior category is Professor Valeria Nicolosi from Trinity College in Dublin, and the junior category prize award for 2021 is given to Dr. Matteo Mitrano. So from Harvard University in USA. I'm really pleasure to introduce both of them, and the idea they will present the topic of their study, the study that was impacting at the international level on the science of matter, on the science of structure of the matter. And they provide a clear advance of science beyond the state of art. Is an active research, so we are not awarding to the career, but we are giving this prize to people which are active in research, and then we're showing in the last 5 years that science is still keep moving and is still progressing well beyond the knowledge we had 5 years ago. I'm really honored about this. And so I just would like to start with a short introduction of what is the Institute of Structure of Matter, Istituto di Struttura della Materia of the National Research Council, and how we arrived to the prize. Let me just briefly show you my screen, and which is exactly, I hope you can see my screen now. And so the Institute is a quite old institute, was one of the first for the CNR, and has three main branches. The headquarters is in Tor Vergata area, which is a research area we call Rome 2. There is another branch in Monte Libretti, which is close to Rome, and we have another branch in the south of Italy in Basilicata, and another branch of the institute is in Trieste in Elettra. So we have 125 employees, 69 research, PhD, postdoc technicians. So it's a quite live institute dedicated, devoted to the structure of matter. So briefly, the mission of the Institute is to develop science of material and technology of matter, to understand their complex properties, and to develop frontier research and scientific concept enabling sustainable technology. Sustainability is an important concept. And as you will see also in the presentation from the two winners, sustainability is also something in their research. There is a strong synergy between theoretical and computational approach, and we present also a multi-scale approach from lab to large facility. Briefly, we are focusing our research in still on the science of matter, but conjugated to a different level, bio, cultural heritage, energy, ICT and security, automotive and aerospace, but we give also a lot of support to deep technology, to basic research, blue sky research. So this is, something that we are promoting very much, in in our scientists and our researchers. So we foresee the application, but we do not discuss also some more fundamental research. In doing this, recently we have set up a platform. So we offer to our researcher and to people that interact with us a platform, a technology platform where science could be developed. We have 134 services, infrastructure that could promote the research, could support the research, and we have 4 branches: theory and models, prototyping, synthesis, and analysis. So you can access all these facilities from internal or from external users, and then you can develop your research with the people of the institute. Among of these, we have, of course, 3 lines at Elettra. So we were promoting developing of Elettra as an institute, and we have UV photoemission line, circularization, and gas phase line. And we are now facing the new Elettra 2.0 that will be almost online in few years. So we will contribute to the development of Elettra 2.0. But we have nice project also for the next future. So we enter in a research infrastructure which is called STACY. So we will implement a cube where we have all the characterization tools in one line. So everyone, we could do all the characterization that are depicted here, and without breaking the ultra-high vacuum. And we are setting up also a pilot fabrication line for new energy generation, storage, and something which is very much related to the sustainability. So this is, in a nutshell, is the idea of the institute. And but we are here for not so much for the institute, but we are here for the winner of the prize. And we will have now 2 introductory talk about the topic that permitted Valeria and Matteo to win the prize. So it's a pleasure for me to invite Valeria Nicolosi to present the talk about processing and application of 2-dimensional nanosheet inks. In these 5 years, she was changing the view we have on the use of 2-dimensional material, mixins, for example, for different application. I was working in mixins, so I really appreciate the starting of the new field she initiated. So it's a pleasure for me to introduce Valeria for this talk, and I give her the floor to start the presentation. Thanks, Valeria.
Thanks very much, Direttore Di Carlo. Thank you very much. For me, it's a huge honor to be here today and receive such a prize. I left Italy 18 years ago, and I have to say I'm still very close, and receiving such a prize for me means the world. So thank you very much. So I will now share my screen. So hopefully you will be able to see now my screen. And I will tell you a bit where my journey started working with 2-dimensional nanomaterials, and where we are moving and what we are doing currently in this field. So before we carry on, I'll tell you a bit about what my group does. And this is very important to set the background to my research, what you will hear later on. So we work around 2-dimensional nanomaterials. We synthesize two-dimensional nanomaterials. We exfoliate them by liquid phase exfoliation. And we do some advanced electron microscopy characterization. I'll show you something later on, because we need to make sure that the materials we make and we exfoliate are the materials we want. And then we push a lot devices. For us, we are very, very applied, and we're pushing devices, especially around the energy storage space, but not only. So the journey with 2D materials started really at the end of my PhD back in 2008, where the group I was working with Jonathan Coleman in Trinity College Dublin, we developed together a methodology to take thick graphite flakes that we bought very, very cheap, 2.5 kilos, a bucket of 2.5 kilos for about 30 euro. And we managed to develop a very easy and cheap and scalable method to select suitable organic solvents, very common solvents that are capable of interacting with the matter in a way that when you provide a little bit of energy or shaking, in this case, we provided that by ultrasonication, you could allow the solvent to get entrapped between the layers and then eventually take the layers apart. So we did develop this for graphene, of course, a material that back then had just been discovered by the Scotch tape method. And we found that really what we could produce was very nice, large, two-dimensional sheets and with a variety of different thicknesses, but the majority of them being a few layers thick. This changed the way we process these materials, of course, and opened a lot of different avenues of what we can in reality do with these systems. Back in 2014, we partnered with a company, Thomas Swan, based in the UK. I was at the University of Oxford back then. And we basically developed with them a method to upscale the production of graphene. And literally, we went from a few milliliters to be produced every half an hour down to about 6,000 liters of graphene to being produced again in half an hour. This was a game-changing type of work, and a report that came out a couple of years ago evidenced that this is now the most common and used method to produce 2D materials worldwide, which is quite, was quite nice to know. With the years, we have basically applied all the things we had learned about graphene and all the processing that we had learned on graphene onto other two-dimensional nanomaterials. Here is just a snapshot, a photograph of some of the types of materials we have exfoliated in liquid. What is the wonderful thing about this is that each different material, each different stoichiometry, each different chemical compound has different properties. So some of these materials will be conductive. Some of these materials will be semiconducting with a whole different range of band gaps. Some of these materials will be insulating. Some would have different mechanical properties. This photo here actually shows the variety of optical properties these materials in particular have, and so forth. So we have in our hands tools that we can use to make devices, and we can pick and choose the material we want processed in liquid so that we can build microscale the device that we like. So this is the fundamental of the science that we develop in my lab. So once we do this, I go backwards. So once we do this, we go on to crucial TEM characterization, because we want to make sure that the materials that we make are indeed structurally sound, that we don't have defects, or that we understand what type of defects or inclusions we might have that might affect the overall performance of devices So this is, for example, one of the very first characterization steps in understanding the type of graphene we were making by liquid phase exfoliation. And we understood some important information. We understood that the materials we make are not perfect at all. In this case, this is an aberration-corrected scanning transmission electron microscopy here of the same graphene sheet a few seconds apart. These two electron micrographs have been taken, and you can see a lot of add atoms, a lot of dangling bonds. You can see a lot of defects. Here is a 5-member rings, and so forth. In this case, actually, the structure rearranged itself in a armchair type of edge a few seconds later, cleaned up basically with the use of the electron beam. All we learned here is that the material was not perfect at all. So if we wanted to use, let's say, graphene for applications, we already knew from this type of characterization that we could not use it for advanced electronics, where you need a perfect device in that sense. You have edges, you have a variety of different thicknesses that might correspond to grain boundaries and things like that. So we knew straight away that what we could and what we could not use this material for. This is an example of molybdenum disulfide nanosheets. We saw in this work that the sheet was actually made of a variety of different steps of different thicknesses. Here was a thicker part. Here you had few layers. Here is a monolayer area. But importantly, we also understood that by liquid phase exfoliation, we formed sheets that were not absolutely homogeneous. So in this case, for example, if you zoom in, you see that the hexagons here are occupied here. The central part of the hexagonal pattern is occupied by an atomic species, by sulfur atoms here. While in this case, you would have a perfect hexagonal type of structure. In this case, what we learned is that you have indeed stacking variations across the different areas of the flake. So again, we learned that we could use this type of exfoliation methodology to make plenty of materials that we could make into composites or other types of applications, but not in microchips, not in not in electronics that was seeking high mobility, for example. In this other work that we published in Nature, and we got the cover in 2010, for example, was on boron nitride. And we discovered that boron nitride was easily doped by liquid phase exfoliation, in fact, with carbon and oxygen type of inclusions. We learned that carbon doublets were always replacing boron and nitrogen pairs, and oxygen inclusions were always substituting nitrogen. Importantly, what we learned was that we could indeed tune the band gap of the material from a wide band gap semiconductor or insulating even material like boron nitride into a semiconducting material with a much smaller band gap, simply by doping it with higher quantities of carbon. So these are all very important things that we learned. This is an in situ TEM video here where you show the formation. This is on black phosphorus nanosheets, and you can see that we have managed to find a way to build and grow in situ wires on the black phosphorus sheets. These wires here are beautifully structured. You see here a wire coming across the layers of a BP nanosheet, and you can actually see how beautifully structured and very repetitive and very ordered these wires are. These are wires that we can grow out of copper. In fact, we have verified that through EELS spectroscopy. So you actually can grow wires that are entirely made of copper, a metal, into a semiconducting material, and you don't have any presence of any oxide or anything like that. This is how these wires, for example, look under two different eye symmetry direction. So the beauty of really making a 3 atoms wide type of metallic nanowire onto a black phosphorus nanosheet. It really opens up a lot of possibility. Beautifully, we have tapped onto our colleagues at Imperial College and Trinity College to do some DFT calculations, and they have indeed verified that these copper wires always grow around the 101 direction. They use the templating grooves of the structure of the BP. And all the structures that are stable are indeed metallic, which has opened up a lot of possibilities for us in terms of applications. So now I want to again focus a little bit on the achievements that we have, what we have done in the last few years, especially in the last 5 years, around applications. And in order to do so, I introduce you a new class of two-dimensional nanomaterials MAXenes. The director De Carlo was mentioning this class of materials. This is really a family of materials. There are about 20, 30 of them. There are transition metal carbon nitrides, carbides, different stoichiometries. The beauty of these materials is that, well, they're not Bandelbas crystals like the ones I showed you before, but these are layered crystals where you have strong covalent bonds in plane and also strong covalent bonds out of plane. So what we do normally is HF etching to break the interlayer bonds, and we go from a max phase that is like that, layered but basically bound together only by covalent bonds, and we transform it into this sort of accordion type of structure where it's a swollen type of structure. Once we do that, we do conventional exfoliation. And the beauty of that is that you can also do it in water, not necessarily in very complicated organic solvents. This is how, for example, we achieve the formation of very nice dispersions that are extremely stable, and we can use simply as inks, as I will show you later. So a little handshake, and here you have a very nice and stable ink. These inks are indeed made of 2D materials that are extremely thin, 1 layer only in thickness, and very, very nice and ordered and pure. So what have we done in the last few years with these materials? So this is one of the earliest works with MAXenes. We managed to actually build a very large area, transparent, flexible, symmetric solid-state capacitors. So we managed to, these materials are beautifully conductive, mechanically very, very stable. So what we see here is a fully assembled supercapacitor device for energy storage, where you have both electrodes, you have 2 electrodes and the gel electrolyte. And whoever works with supercapacitors know that it's very easy to build very small micro supercapacitors, but once you actually have large area supercaps, they don't work very well. In this case, we actually, because of the electrochemical performance of MAXenes, their electrical conductivity, and their mechanical stability, we managed to assemble very, very large area devices, fully transparent, 98% transparency. Here, this device is overimposed on my postdoc mobile phone to show full transparency. And indeed, we show that they really perform well as supercap. You can indeed store energy, and they're also very good in terms of rate performance. You can push them up to 500 millivolts per second to actually start getting some sort of resistive behavior. So very high rate charging and discharging performance. More recently, because we have such beautiful inks, they're very, very processable. So we thought, how well, we need to develop something that allows us to test these inks in a very fast, that allows us to prototype things very fast. So we built this methodology where we can print by 3D printing, fused deposition method, just conventional stamps, and you can give the geometry and the design that you want. When we do supercaps, we love interdigitated structures. Those are these stamps here, or you can be a little bit more fantasious and just open up your freedom in your mind. And basically, you can make the stamps of the shape you like. Once you've made the stamp, you only need to dip the stamp into your ink, and you can stamp away your device on any substrate you like. In this particular case here, we printed onto paper. We also can do like the Babylonians did, and basically also develop something that is super fast in prototyping. So we printed by fused deposition method rolls rather than stamps, and literally use that, like the Babylonians did to produce their art, to actually produce in a very, very fast way many prototypes. The nice thing that we realized is that not only this was very fast, but indeed that worked extremely well in terms of supercapacitor performance. And again, you can push a fairly high rate performance here. To get some resistive behavior, you have to push at about 100 millivolts per second. Because we can process these materials in inks, and then again, these are inks without additives, without any stabilizer. They are just as made as I showed you before. You can easily print them. So we have developed methodologies to do extrusion printing or inkjet printing of devices, and then it really works quite nicely. You can print devices. Here is using Maxine inks in organic solvents. And in this case, we do inkjet printing, and you can use interdigitated geometries. You can print in series, you can print in parallel. You can really open up your imagination and just use the advantage of the freedom. Well, we saw that only after 5 passes of printing, you can actually have a massive conductivity of about 3000 Siemens per centimeter. And again, the conductivity did not drop even upon bending. So these devices were fully bendable. And this is an example of the devices that we printed from water by extrusion printing. And then again, you can use interdigitated structures. You can print other types of less geometrical rigorous type of structures. And again, they really, really perform because you achieve very, very high conductivity only with a few printing passes. The devices are very stable and resistant after you print them. Here is a test by Scotch tape on a device, and you see that actually you can try to peel off the layers of your device, and actually you don't get any residual. They're very sturdy. And if we compare their performance, here in red you have the performance of the extrusion printed supercaps, and here in blue the performance of the inkjet printed devices in terms of aerial capacitance, as compared with a lot of literature out there, similar devices in terms of thickness, area printed, and things like that. You can see that these devices truly outperform anything that had been reported up to that stage in 2019 at least, but I think it's still quite a record. So this is a Ragone plot where we show the energy density, how much energy these devices can hold as a function of power density, how fast they can charge and discharge, and again, as compared to a lot of similarly produced devices with other materials. And in terms of performance, we are up here, so we can store quite a lot more energy as compared to other devices. Also, they are fully bendable, and you can see that there is no decrease in electrochemical performance by bending. We've also used these materials in battery technology, and we decided to try actually to start from a material, an anode material, silicon, that has been a very highly recommended and suggested material in the battery field for quite some time, for at least 10 years at least. And why silicon is very good, because, well, silicon can accept up to 4 lithium ions as opposed to 1 that currently graphite anodes can take. So has a very, very high theoretical capacitance. The problem with silicon is that when you charge and discharge silicon nanoparticles, in this case, the particles goes through a volumetric expansion and then compression of about 400 times their volume. And when you go through that, the particles themselves start cracking and getting degraded. And then eventually, if you do that a few cycles, then the electrode starts pulverizing and starts losing their performance. Our strategy, well, normally what you would find in the solutions in the literature would add a polymeric binder to mitigate this volumetric expansion, and also they add carbon black as a conductive agent to maintain the performance of the electrode. Our solution instead was to really replace both the carbon black, the conductive agent, and the polymeric binder with MXenes. So what we simply developed a methodology to mix silicon nanoparticles, MXene inks in water, do a slurry, and then cast this slurry exactly how battery industry does. And what we realized was that the MXene sheets were organizing and self-assembling themselves into blankets, in 2D blankets that were surrounding the silicon nanoparticles. This was really nice because not only they managed to provide electrical conductivity to the electrode, but also managed to completely mitigate the volumetric expansion and compression of the silicon throughout cycles. And by doing that, we managed to achieve very, very high record thicknesses. And of course, the thicker is the electrode you can make, the higher is the capacitance that you can achieve. For example, with MXenes, we arrived up to 800 microns in thickness. Without MXenes, with the polymeric binder and carbon blacks, we could achieve maximum 280 microns. And after that, the electrodes themselves start failing. They just go above critical crack thickness. Do these devices work? They work very, very well. We published this in Nature Energy a couple of years ago. Only by adding 30% of MXenes, you do have an improvement in conductivity of about 1,200 times. And if you look at the tensile toughness, well, you can actually get, again, with about 30% of MXenes, you achieve about 40 times tensile toughness, which is quite of a record. And that is what ensures the mechanical stability of the electrode. By doing that, we could achieve a record aerial capacitance of about 12 milliamps per hour per centimeter square, and theoretical capacitance of about 3,200 milliamps hour per gram. Very nicely, if you look at the aerial capacitance as a function here of the mass loading of MXenes here, here the dotted line is what the traditional standard commercial batteries can perform, about 4 milliamps hour per centimeter square. In blue and red here instead, you see the performance of these devices. So we managed to actually hit a record performance only by adding about 30% of MXenes. So we were capable of delivering high aerial capacitance and very, very minimal mass loading. Last but not least, I would like to show you a few of the very latest results coming in from my group on a different type of application. We have been actually using MXenes, mixing them with polyacrylic acid, and we've formed some very interesting hydrogels, which are very stretchable, malleable, and also printable. And they have a very nice porous structure. And we've been using this, the actual actually self-healable. Immediately they heal together. You can see how stretchy, bendable, and healable they are. And they can take basically the shape of the device where they go. We've been using this for MI shielding, to shield radiation. Also, they are electrically conductive, being made of MXenes. And here you see how a little cut, it's interrupting the circuit, and then it heals immediately, and it starts, the circuit is back. So we've been using that in terms of for MI shielding. Here is, for example, the a terahertz signal here when the hydrogel doesn't have any MXene, but with only 6.5% in weight of MXene in the hydrogel, we can already screen most of the radiation, and with 8.5% in weight of MXene, you get a full screening of this of terahertz radiation, which is very, very efficient. The reason is because of the cavities that we have in these hydrogels. So the radiation goes in and it starts to be scattered repeatedly until you get the transmitted waves is basically totally screened. The beauty of that is also the versatility of these devices, because they're made of MXenes, they are conductive. So we can indeed kind of see how the conductivity changes as a function of straining. And then after doing that, we've been using them as sensors. So here, for example, this hydrogel is on the finger of my postdoc, and we were capable of detecting the bending of the finger. Here is placed on the arm of my postdoc, and you can detect the bending of his arm. Here is placed on his throat, and it was capable of detecting all the different phases of swallowing. Motion sensing here for the frowning of the head. Here we were capable of detecting water droplets being dropped onto the device. And also we could write on devices like this, on these hydrogels, simple words, but still we were capable of detecting writing. So here we wrote okay, here we wrote no, and here we wrote yes. These hydrogels are also fully printable, and the beauty of that is that, imagine, well, we hear a lot about 5G radiations and things like that. Well, you have the possibility of using 3D printing to print the screen, the case, capable of shielding any radiation depending on the object and the device you have. So you have a lot of form factor and freedom of operation. So without further ado, basically I finish here my talk. I hope I've shown you some of the possibilities that you have working with two-dimensional nanomaterials. I've showed you applications around energy storage, MI shielding, but not only. And thanks again for listening and for this invitation and for this wonderful prize. Last but not least, I would like to really thank my group, all the people who have made the success of this group being possible. The collaborators, again, together we achieve more. We cannot do everything on our own, and I really hope that this prize will open the possibility of a lot of nice collaborations with the CNR. And I would like to thank all my funding bodies, Science Foundation Ireland, the European Research Council with the 6 different awards that I have from the ERC, a lot of industrial partners, Kenwood, Lego, some companies in the Formula One that I cannot mention, Enterprise Ireland, Nokia, and so forth. And with that, I thank you all for your attention. Thank you.
Thanks a lot, Valeria, for this impressive talk and results, actually, and how the science really is improving thanks to your work and your collaboration, of course, with many people. So now it's open for questions. I forgot to mention that we can post questions in Facebook, and then I will read questions from Facebook. So I could start, to ask you, being involved in MXenes mainly for work function changing. So how easy is to master the functionalization of the of the vaccines. So since you can move the work function from 2 electron volt up to 6, me as device engineering, so we'll really like to have something to control this work function. Is it easy or not?
Well, actually, functionalization of vaccines is one of the fields that is ramping hugely. And the reason is vaccines, because they are etched and because they come from a little bit of a trickier processing at the start, they have a lot of functional groups. And these really open the possibility for tuning the properties quite nicely. And I think the bondings there, that the functional groups OH that are present all over the surface really open up a lot of possibilities. So it's a huge field that is coming up, and there is going to be a lot of nice work coming.
Oh, that's great. And just to take the occasion that there are the people did not know about the Facebook questions, so maybe we can return on your talk at the end. And what about the oxidations? One of the problems I have to face is the oxidation. It looks like that, I mean, you solved the problem somehow. So if you can tell, of course.
Absolutely. So I can tell you, before starting all the fun work on devices and printing, we spent about a year and a half on understanding how to store vaccines. So the trick actually is, once the vaccines themselves are only degradable and they get oxidized in water environment when they have water-rich environment. So if you etch your material and you have a dispersion, we managed to understand how to store it. So you have to store it in the fridge. Temperature is a very, very important factor. And you need to pump an inert gas in the rest of the vial. So substitute the oxygen with nitrogen or something and store it in the fridge. And we have dispersions that we keep for months in the fridge without any sign of degradation. Once you print them and the solvent is evaporated, water is evaporated, devices are super stable. We have no problem whatsoever. Once we print the devices, we can test them after a year and they're still perfect.
Oh, that's great. Oh, thanks. Thanks. Apply immediately. Okay, so at the moment there are no other questions, but we will return back to you if a question will show up. And okay, now thanks a lot, Valeria. So unfortunately we are not in presence to cloud, but now we move to the second talk. For the second winner of the prize, of PRISM Prize, is Matteo Mitrano from the Department of Physics of Harvard University in USA. Welcome, Matteo. It's really a pleasure to have you here today. And so we will, Matteo will speak about probing-driven quantum phases of high-temperature superconductor with ultrafast X-ray. So we need to mention that I mean, Matteo was leading, important, impacting publication in the last 5 years on possible light-induced superconductivity in C60 with potassium at high temperature, and this was really driving a lot of research and was really innovating, was shifting the knowledge on the field at the international level. So thanks a lot, Matteo, for your contribution to the science, and the floor is yours for the presentation.
Thank you, Aldo, for the introduction. Can you hear me?
Yeah, perfectly. Yes,
perfect. Well, first of all, I would like to say that I'm honored to be invited today and to receive this award by my national community. Where they gave me the possibility to start this career in science. Today I will tell you about some work that came after my studies on superconductivity in organic materials, but always a work focused on understanding how the microscopic physics of these light-matter interaction processes occur with respect to the manipulation of superconductivity in a variety of what is now called the realm of quantum materials. So let me just say that this story, the story of this talk, is really a snapshot on what is the latest research going on in understanding how to manipulate materials with laser pulses. So over the last couple of decades, a number of research groups have devoted considerable effort and in achieving results related to the manipulation of quantum phases in materials, and with the ultrafast lasers. So as we have seen in the previous talk, you can control the materials properties, as an example, by exfoliation. You can apply other stimuli like pressure, electric fields, and so on. Here we are looking at what happens when you shine intense laser pulses onto technologically relevant materials. And over the last few years, this has led to the observation of so-called hidden phases, states of matter that are metastable but not present in the equilibrium phase diagram of certain solids. It has led to in general to the possibility of realizing ultrafast switching of photoinduced phase transitions, insulator to metal transitions, as an example, charge order transitions. Lasers have also been used to directly manipulate and engineer the band structure of materials through processes of coherent dressing of electronic states by means of the vector potential. And finally, it has been possible to manipulate magnetism at ultrafast timescales to switch ferroelectric materials. And finally, what is really the topic of this talk, it has been possible to induce superconducting-like behavior in materials far above the equilibrium TC, and this in a variety of solids. So let me just say that in general, when we think about light and superconductors, we think about thermal heating. But actually, there is a long history of studies in which it has been practically investigated whether light can be used to stabilize superconductivity. So superconductivity is this very interesting state of matter in which electrons pair and lead to a state with zero resistance that is very appealing for lossless power transmission, nuclear fusion, magnets, and so on. The important thing that has been done over the last century is that in general it has been possible to use electromagnetic fields, first of all in the microwaves, to actually clean incoherent carriers out of the gap and enhance the performance of superconductor. This was already done in the 60s and in the 70s, but led to very small enhancements of the resonant TC. More recent of the critical temperature for these transitions that are typically found at very low transition temperatures. More recently, the group where I performed where I got my PhD, led by Valeria Nicolosi, started investigating whether resonantly exciting certain vibrations of materials and deforming the structure of materials could lead to optimized superconductivity. One pioneering experiment that was performed in 2011 by Daniele Fausti and Andrea Cavallari was that in a particular couplet, it was possible to use laser pulses resonantly tuned with a distortion of the lattice, with a vibration of the lattice that corresponds to a distortion, copper oxygen octahedra led to the observation of superconductivity, of enhanced superconductivity out of equilibrium in a material less CO, where superconductivity at equilibrium is quenched by the presence of so-called charge order. And I will come to this phase later in the talk. But essentially, you have the doped holes that should conduct electricity in these materials tend to self-organize in stripes, in metallic and insulating rivers, therefore quenching transport. And superconductivity doesn't occur naturally. By distorting the lattice, these researchers were able to show transient signatures of superconducting coevents seen as tunneling along a certain crystallographic direction. Now, this phenomenon was then detected over many years in other materials, in YBCO as well. That is another cuprate with double layers. In LBCO, that is another more cuprate, and then some sort of a big shift in our thinking about this phenomenon that seemed somehow restricted to the cuprate. To the cuprates was my observation of gapping and so potential light-induced superconductivity in K3C60. And therefore an organic material that is very structurally different with respect to the cuprates. And more recently, other researchers at Max Planck in Hamburg also found signatures of enhanced superconducting coherence in other organic materials with two-dimensional character. The fact that this phenomenon is seen in materials with such a different structure and such different electronic properties bears the question of whether there is a fundamental microscopic mechanism that accumulates all these experiments and all these manifestations of light-induced coherence, and therefore prompts the investigation of the fundamental microscopic light-matter interaction that leads to this enhanced coherence out of equilibrium. The main issue that we have from an experimental point of view is that right now, the way we diagnose photoexcited superconductors is essentially through time-dependent transport. So we either perform time-resolved optical spectroscopy in the terahertz range. These are, as an example, my data on K3C60. And as we have seen in the previous talk, terahertz can actually tell you a lot about the screening and the conduction properties of these materials out of equilibrium, or you can perform transport at ultra-fast timescales, therefore measuring the resistivity of these samples. The problem with these probes is that they don't really tell you. They are long wavelength probes, so they don't really tell you what is happening in the material at very short wavelengths, and microscopic length scales, because they are Q integrated, like transport or Q equals 0. In Q, where Q is the momentum, or Q equals 0 observables. So the next step is that we have to find a probe to measure the microscopic behavior of these materials throughout the Brillouin zone. And we therefore need to measure the microscopic dynamics of non-equilibrium and light-driven superconductors at finite momentum. And in particular, this is desirable because we can learn about the propagating collective excitations of these materials. We can learn about coupled degrees of freedom, so we can learn about whether there is interaction between spin and orbital degrees of freedom, spin and charge degrees of freedom. And we can follow the dynamics of microscopic order parameters. So if there is an order parameter, if there is a phase with some sort of short wavelength order, we can actually follow that. The question is, how do we actually measure these microscopic properties out of equilibrium? And the way we do this is actually with the newly developed technique that is time-resolved resonant inelastic X-ray scattering. So resonant inelastic X-ray scattering is a at equilibrium a well-established technique that allows to study the behavior of valence electrons. It has been developed over the last 20 years. A big part in the development of equilibrium rigs has been done by Lucio Brajkovic and Giacomo Ghiringhelli in the Polytechnic in Milan. And essentially, in the non-equilibrium incarnation of this technique, we can follow the dynamics of a material that is driven out of equilibrium with an optical pump, and they're probed with X-ray pulses with a certain momentum, with a certain energy that excite core states into the valence states, and then we emit, and then we combine by emitting a photon with a certain momentum kf and a certain energy omega f. The difference in momentum and energy tells you about the nature of the excitations in the driven state. And the fact that we can use X-rays is actually really important, because the fact that they are resonant to a certain atomic absorption gives you a boost in intensity that is much needed, but also valence band sensitivity. So you can really follow the dynamics of the low energy states close to the Fermi level that really contribute to the transport properties. In addition, the fact that you are using X-rays gives you, with high energy, gives you the possibility of sampling properties at finite momentum. So you can really investigate the microscopic physics. The way we do this is by using particular accelerators that are so-called X-ray free electron lasers. This is, as an example, an image of the LCLS free electron laser. The LCLS is a 3-kilometer linear accelerator with an ondulator of I don't remember exactly, but approximately it's with an ondulator of order 150 meters that generates very intense X-ray pulses ranging from the soft X-rays to the hard X-rays, with a duration that can go down to a few femtoseconds. And there is work currently to go beyond a sub-femtosecond into the attosecond regime. At the beginning, the LCLS has been the first free electron laser. Right now, there is many more in construction or fully operational. There is SACLA in Japan, Pohang in South Korea. There is more, the European XFEL in Hamburg, the Swiss FEL. Elettra in Italy is an important FEL. It has been the first seeded FEL. It doesn't operate in the hard X-rays. It's a UV soft X-ray FEL, and is also doing pioneering work with respect to this technique. So I will focus now on one specific scientific case, that is the issue of photoexcited superconductivity in lanthanum-barium copper oxide. Lanthanum-barium copper oxide is the original superconductor discovered by Bednorz and Müller in 1986. This material is particularly interesting because at equilibrium, superconductivity at 1,8 doping is strongly suppressed by the presence of a competing order. The way we detect superconductivity in this material is by looking at the reflectivity. This is the reflectivity along the z-axis, and we can see that when the sample goes superconducting, there is a plasmon along the z-axis that corresponds to the tunneling of Cooper pairs along the out-of-plane direction. These are layered materials, and you have transport along the out-of-plane direction. We can see in this material, in the Cavallari group, there has been reflectivity studies in which you start from a state where superconductivity is either suppressed or absent. And by shining laser light at 1.5 eV, it was possible to show a blue shift of these resonance corresponding to an enhancement of tunneling along the Z direction, along the Z axis, both below and above the superconducting TC. The way we want, so this phenomenon can possibly be understood in terms of a competition with another order parameter. And what we know in this material is that there is actually a competing order that is essentially a density modulation of these carriers. I told you that carriers tend to self-organize in this unidirectional structure, in this unidirectional charge density wave, with a wavelength of approximately 4 unit cells. And this density modulation behaves like a diffraction gradient, and so can be characterized in terms of diffraction peaks in momentum space that are at finite momentum, because here the wavelength is approximately 13 nanometers. So optics is definitely not able to interrogate this competing order, but we can monitor this competing order and understand what the laser is actually doing to the material by using X-rays that can reach out to these peaks at finite momentum. So what we did is that we during my postdoc, I've been able to perform the first time resolved Rix measurements on this material. And we decided to investigate the charge dynamics of lanthanum barium copper oxide following laser excitation that brings this enhancement of the C-axis tunneling. And this is the first Rix spectrum taken on this material at an FEL. And before I start discussing the dynamics of this spectrum, let me just tell you that there are 3 dominant spectral components that one has to take into account. Here we are looking at the material at equilibrium, and we have one elastic feature that is corresponding to this diffraction of this charge density wave modulation. We have then 2 inelastic features related to so-called DD excitations. These are excitations between the orbitals, and charge transfer excitations that correspond to really charge transfer between copper and oxygen orbitals. Now, what we decided to do is that we performed the study in which we excited the material with strong laser pulses and followed the behavior of this competing order at finite momentum in the charge sector. And what you can see here is the first scan of the dynamic of this material out of equilibrium. So here you can see on the lowest side of this plot the 3 features at negative time delays before the pump arrival. We can see here at 0 the charge order peak, and here the inelastic features. So here this is the charge order peak. Then we have the DD excitations and the charge transfer excitation that is fainter. And we can see that as the pump arrives, the charge order is disrupted and then recovers on a picosecond time scale. And what you can see here on the right of the screen is actually the possibility of, is actually a first movie of the dynamics of this order parameter. So we can really see this peak at zero energy loss that is suppressed by the pump, and then recovers really slowly. And I will tell you more about the recovery in a second, but just let me tell you that this is really the first time that we have been able to make a movie on a picosecond time scale of a non-conserved order parameter at finite momentum in these materials. And the recovery is extremely slow because in order for this order parameter to form, it has to annihilate topological defects that are really hard to get rid of. Let me say one important thing. If we focus on these short-term dynamics and we start sampling the short-term dynamics as function of momentum, so we start scanning it in momentum space, we can actually see that the time it takes for the order parameter to go back to equilibrium is not constant. It actually varies with momentum. And the fact that it varies with momentum tells us that the recovery is faster when you go out of the diffraction peak and when you go into the tails of the diffraction. And if you plot if you extract the time constant from this exponential relaxation, and you plot the relaxation rate as 1/tau as function of momentum, you can actually see that this relaxation rate goes quadratically with momentum, therefore telling you that the recovery dynamics is diffusive. So what is happening in this material is that the palm pulse is removing the competing order, and the competing order then reforms through Brownian diffusion and self-organizes again. And this actually sets the time scale for the lifetime of this light-induced state, in which you are removing a competing order that is robbing states at the Fermi level for superconductivity to appear in this material. Now, this is actually one important observation that we can make by applying time-resolved rigs. But there is something more to that. The laser is not just removing a competing order, but is also possibly modifying the electronic structure of this material. And therefore, the next question is whether the electronic structure of LBCO, of this high-temperature superconductor, is modified by the application of a laser pulse. So again, we looked at the scattering process. We now make use only of the first part of the scattering process, that is essentially an X-ray absorption, and we probe with this the electronic density of states of this material. And the density of state of this high-temperature superconductor at Fermi level are essentially determined by copper and oxygen orbitals in plane that also hybridize in a state that is called usually Jagger singlet. So this tells you, when you start plotting density of states close to the Fermi level, you have essentially the d orbitals that tend to split because there is correlation. You have to pay an energy cost of order u for putting two electrons on the same site. This is Coulomb repulsion. And then we have the p orbitals that lie in between the d orbitals, the lower and so-called lower and upper rubber band. And then we have one hybridized state here in the middle. And when you start doping it, you have that the Fermi level falls in the Jagger singlet. The key thing that you have to keep in mind for the interpretation of what comes now is that by absorbing X-rays from core states, we can actually induce transitions into unoccupied states and therefore measure the unoccupied density of states of this material. We can send electrons into the Jagger singlet, into an unoccupied portion of the Jagger singlet, or into the upper rubber band. And we performed X-ray absorption spectroscopy at the oxygen K edge and the copper edge. And at equilibrium, what you see in this material at the two edges are peaks that are quite well defined. So you have at the oxygen K edge one transition for the Jagger singlet. You have one transition for the upper rubber band. The upper rubber band is really prominent at the copper edge. And what we find when we start doing our dynamic experiment is that we start with these peaks at equilibrium, the Jagger singlet and the upper rubber band at the oxygen K edge, the upper rubber band at the copper edge. We excite the material with the laser, and we see that the upper rubber band is actually redshifting and is changed by the application of a laser pulse on extremely short time scales. This happens essentially instantaneously and decays in over time scales of the order of a few hundreds femtoseconds. While the Jagger singlet is unaffected. So this is actually really important because it's telling us that the electronic structure of this material is changing. And we can actually rationalize this by mapping this electronic structure onto a 3-band Hubbard model. That is the minimal model that allows us to describe the electronic response of this material to X-ray absorption. The punchline of this analysis is that if we systematically vary all the parameters of the 3-band Hubbard model, we discover that the only parameter that actually reproduces our observation of a fixed Jagger singlet and a moving upper rubber band is a dynamical change to the on-site Hubbard U. That is essentially the energy cost of putting two electrons onto one single copper orbital. Any other parameter would shift the Jungreis singlet. So we are dynamically altering the band structure. And the extent to which we are doing it by looking at the slopes of these dependencies is approximately a change of 140 millieV. That is actually a sizable change for a modification of an electronic interaction parameter in these materials. We can also reproduce this with a full simulation of the dynamical response of the absorption spectrum. Here we apply exact diagonalization in a time resolved setting. We downfold the model to a simpler model with essentially a single band to keep the computational complexity manageable, because we are following the full time dependence of the response, and we implement an excitation with a laser pulse with an electric field of approximately 10 megavolt per centimeter. These are ordinarily the fields that we are using in this kind of experiments, and we can see that the distance between this lower and upper rubber band is actually decreasing as function of time. And if you take line cuts at negative time delays before the pump arrives and in the middle of the pump excitation where the electric field is maximum, you will see that actually there is a red shift of the upper rubber band. So we are actually even demonstrating from self-consistent calculations with exact diagonalization at a fundamental level that the action of the laser is to close the upper rubber band due to a renormalization of the onset Coulomb repulsion. Now, why this is important? With this, we are demonstrating that lasers, ultrafast lasers, actually can be conceived as a microscopic tuning knob for light-driven quantum materials. A reduction of the aberration in the cuprate is particularly impactful because in this material, this decreases the charge transfer gap. The charge transfer gap is anticorrelated with TC. So in principle, a lower charge transfer gap will increase could increase the equilibrium TC and perhaps favor pairing out of equilibrium. Most importantly, if we are reducing the aberration, we can actually affect also the spin wave energy and renormalize the pairing interaction. If we believe that the copper oxide are actually materials in which superconductivity is mediated by spin fluctuations, then we expect the energy of the spin waves to change between the equilibrium here in black and the transient state. And this can be captured as an example by linear spin wave theory. That is essentially an expression, a closed expression for the renormalization of the exchange interaction. That is the fundamental energy cost of swapping two spins on different sites. And you can see that this quantity depends on the aberration that we are changing these materials, and this is a mechanism that could also be functional to the discovery of ladder phases, not just for the enhancement of superconductivity out of equilibrium, but also for the discovery of driven spin liquid phases or eta pairing condensation. That is a special kind of superconductivity of staggered electron doublons and holons in the lattice, and this physics the observation of this physics, in particular the modification of spin waves and of ultrafast magnetism in quantum materials, will be enabled by a new generation of high-resolution spectrometers that are now under construction and deployment, as an example at the LCLS2, this accelerator in California, or at the European XFEL in the very near future. So this is where the field is going, and where the next exciting discoveries lie ahead. And with this, I'm concluding. Before yielding my time, I want to just acknowledge that this was work. This was the result of the work of a number of people. Here, there is my group at Harvard University. In particular, part of this work that you've seen was performed by Denitsa Baikusheva, my postdoc, and calculation done by Yao Wang at Clemson University. And previous RICS experiments have been performed together with the Abamonte group at University of Illinois Urbana-Champaign, and to various collaborations with scientists at PostTech, at Stanford, SLAC, and samples from Brookhaven National Laboratory at NIST, and so on. With this, I thank you all for your attention.
Thanks a lot, Matteo, for the very beautiful book and also the innovative approach you were using for your study. I mean, light-induced superconductivity, as you said, was already addressed, but you were addressing a different way. So it's also very difficult to change the paradigm. And congratulations for what you have done in the field. So there are questions. I mean, I just read one question. During the optical laser pulse excitation, is there the chance that any interference electromagnetic field can be involved during the process that should be taken into account, such as scattering or surface plasmon polaritons?
I think this is so. This is a very interesting question. I would say.
I'm from Antonio Sant'Agata. Sorry.
Yes, thank you. So I would say that in general, this is a question that always needs to be considered and kept in the back of our minds. For what concerns these specific experiments with resonant inelastic X-ray scattering, I would say that the penetration depth of the X-rays is such that, as an example, surface effects like plasmon polaritons are not enough to justify. Would not have enough cross section. Would be not dominating the cross section, so it would be difficult to detect them. This is especially the result on the dynamics of the charge order or the parameter. This is more of a bulk effect. For what concerns optics, I would say if you were to do as an example time-resolved Diels experiments, that would be definitely something to be considered in looking at the spectrum of the bosonic excitation pseudo equilibrium. I cannot see these as an important factor for, as an example, the observation of charge order at 1/4 of the Brillouin zone. The other thing is that plasmon polaritons are also very relevant at very low momentum transfer.
Thanks, Matteo. And is there any suggestion about what kind of structure could show this light-induced superconductivity? Because as far as I remember, I mean, you showed that. I mean, this is better. I mean, if you go below TC, you suppress a bit the effect, and if you are above, you get the effect. So is there any prescription of the material that maybe could not have a clear TC, but then could have light-induced superconductivity?
There has been a number of developments in the last few years since my original work. So it seems that there is a correlation between the presence of the Nernst effect in some of these materials and the possibility of enhancing superconductivity. But I would say this is actually the pressing question that we are trying to answer by performing these experiments. In general, as of today, a microscopic theory of the phenomenon is lacking. At the very beginning, we had an intuitive picture of what was going on for layered compounds. But this was definitely not the case for the buckyballs, because in C60 you have that the physics of the pairing interaction is so different with respect to the cuprates, and it's definitely let's say a phonon-driven superconductor. Even though there are some caveats, and there has been considerable work by, as an example, Massimo Capone, and others on how to interpret the behavior of these materials. But I would say in the last few years, the correlation with the Nernst effect is one of the most promising directions. Based on the results of our experiments, if you can find materials in which you can dynamically enhance the spin fluctuation spectrum, that's also another possible prescription. If you can increase the characteristic energy of the spin fluctuations, that could also be a beneficial effect.
Thanks, Matteo. I have a couple of questions from the Facebook to Valeria. And Valeria, so one is, what about thermal properties of MXenes? Their conductivity can be tuned as well as band gap and warp function. Did they test MXene only at room temperature or also at higher temperatures?
So absolutely, the properties can be tuned. We were talking before about functionalization as a tool to tune band gaps, and also thermal properties can be tuned. There is not so much work being done, but I mean, it's a relatively new class of materials, so there is a lot of exciting work ongoing. And then the second question was about testing at different temperatures. We have been testing our supercaps at different temperatures, and all these works are ongoing. But in general, I think there is a lot of work that will come in the next few years in understanding the behavior of MXenes at temperatures below room temperature and above, and see how the properties fluctuate. There is a lot to know.
Thanks. The last question is related to batteries. Are MXene being used also for other kind of anodes or even cathodes in batteries?
Yeah, there is a lot of work being published. They have been used in sodium-ion batteries, lithium-ion batteries, all solid-state batteries. There is a lot of exploratory work in using MXenes as a battery electrode as opposed to an additive, as we did. The work that I showed was mainly was a work that we did with and for industry. And they wanted a fairly upscalable anode material to be used, such as a silicon. And we showed that the performance of the electrode could substantially be improved by adding minimal percentages of MXenes. Nevertheless, there is a lot of cascade work coming in using MXenes as electrode material for both lithium-ion, sodium-ion, lithium hair, and a lot of different types of works, definitely.
Okay, I do not have other questions. Thanks really a lot. And now we move to the prize. Okay, I share my screen. Okay. Good. So it's really a pleasure now to move to our ceremony. It's I just briefly mentioned how the prize has been, how the winner has been selected. So I was not part of the selection, so it's really come independently on me. And I'm really happy about this because it has been defined by the researcher of the Institute. So all the researchers of the Institute has been proposed me the nomination, and there a commission made by platform responsible and site responsibles were then collecting all the nomination and making a rank, and then selecting the two winners. So as you can see, it's a process made by researcher, and for what they have seen, for the work that's been steering their research as well. So it's quite, it's a really something that is going to a real work on the field of science. So with this introduction, I move on to the first prize. The first prize, the Institute of Structure of Matter of CNR Award, the PRISM 2021 senior category, to Professor Valeria Nicolosi for the breakthrough achievement in the past 5 years in the field of science of matter. So I really congratulate with you for the incredible work you have done. Congratulations, Valeria.
Thank you very much, and thanks for this wonderful prize. I'm really touched, and I truly hope that this will bring a lot of collaborations and will bring me closer to the Institute, and I'm really touched, and thank everyone. Thanks.
Thanks, Valeria. I will, as you see, there is a prize, there is a pergamena, but there is something also, an action activity. I will tell the winner at the end. So I move to the second prize. So the Institute of Structure of Matter of CNR Award, the PRISM 2021 Junior category, to Dr. Matteo Mitrano for the breakthrough achievement in the past 5 years in the field of science of matter. Congratulations, Matteo.
Thank you, Carlo. As I mentioned before, it's really special to receive this recognition from my national community and from CNR, and I really hope that that after 11 years working abroad, this will be the opportunity to establish fruitful collaborations in the future. Thank you.
Thanks a lot, Matteo. That's one part of the prize. In fact, I mean, beside the pergamena and the prize, that I will, don't worry, I will ship all this prize to you. I hope that soon we will return to offline prize, but nevertheless, I mean, beside the prize and the pergamena, the idea of the PRISM, which is, as you say, as you have seen, is really an active, ongoing activity. So we give the hour to you for the activity in the last 5 years. Of course, you have done a lot even before, especially Valeria, but also Matteo. As I said, he was working 10 years out of the community. So. But as I said at the very beginning, this prize is for what you're still doing. I mean, you have done a lot, but you are keeping the science moving on to the frontier, beyond the barrier, beyond the knowledge we have. So it's really a prize for the intense activity you are still doing and you will do hopefully in the future. For having this in mind, we would really like to offer the possibility to interact and use the capability of ISM, of National Research Council, to perform a research activity. So together. So we are proud, I mean, to collaborate with you. And to sustain a research that, I mean, could start, I mean, as a a sign of the PRISM award. So this is more or less what is the meaning of the PRISM. Is something that is moving, is running, and it will develop even further in the future. I also ask you, I mean, as a winner of the first edition, to be part of the commission for the next PRISM edition. So we will have an edition in 2022 as well, and very soon we'll start the nomination and then selection for the prize, for the award. So if you like to accept, it would be really an honor for us to have you in the selection commission. I want to say that the PRISM is an international prize, so there were many nominations, also not Italian nominations. So then, as you see, it's by chance you are two Italians, but I mean, in principle, it's quite international prize. Okay, good. I think we can conclude here. I really like to thank also all the people that were involved in setting up all this prize, the people from communication office of ISM, and all the researchers that were making the nomination, the commission that was selecting the very outstanding winner of the prize. Okay, thanks really a lot, and I hope to see you soon, or in Italy as well, also somewhere in the world, but also in Italy, maybe in our institute to discuss science together. Thanks a lot.
Thank you very much. Thank you.
Thank you, Aldo, and congratulations to Valeria as well.
Okay. Bye bye. Take care. Bye. Bye.
Take care.